Hello everyone, this is David Motorca speaking, and I will be introducing the Climate Data Analysis Program. The purpose of this program is to analyze climate data to further understand the effects of climate change, specifically in counties and states in America. This is done so by generating graphs from climate data such as average temperature, precipitation, and maximum and minimum temperature. These graphs then allow us to look at the data and identify patterns to better understand what the future will look like in terms of the climate. Furthermore, it can be used as a tool to better understand how individuals or smaller communities will be affected by climate change rather than the globe as a whole. Hello everyone, this is David speaking. I'm going to bring up a recent example that is a bit broad but really highlights the usefulness of this program and its potential for the future. California experienced the worst droughts in over 100 years during January, February, and March of 2022. As you can see in the slide, many parts of California were in the extreme drought, while the rest of the state was experiencing severe drought. If we fast forward to this year, California has experienced and is continuing to experience major flooding from record breaking rainfalls. Some areas of the state are even seeing double their average precipitation compared to the historical average for this stage of the water year. This type of anomaly may be more common in the future as weather intensifies, which is why it is so important to analyze specific counties and their weather patterns as opposed to the Earth as a whole. To be clear, we are not trying to disprove that the Earth is warming, but rather wanting to investigate and analyze why certain counties are experiencing drastically different levels of warming and cooling. This is all to get a better understanding of how individuals may be affected by climate change in the near future and in their respective communities. Hello everyone, this is David Motorca speaking, and now I'll be doing a quick demo of how the program operates, just because my fellow teammates are going to go much further in depth and explain the main features and functionalities that we have implemented and improved. To begin, we're going to select a state from the drop-down menu, and for our sake, I'll just do Oregon, and let's do all counties just so there's a large data pool. As you can see, it gets populated into the table, and for our sake, I'm going to leave the date range and begin and end as default. Now I'll click on Align, and I have to select an equation after that, and I'll do linear for now. I might change it later in the demo, and I'll do precipitation just because I know we love the rain. Now all we have to do is come down to the bottom and click Graph It, and you can see it's working when you see the dotted lines, and a graph appears. So it's pretty straightforward, and if you want to change and modify the graph, you're free to do so without having to re-input everything. So let's say, for example, I want to change from linear to quadratic. You simply click quadratic and then come back down and regraph it. And there we go. You can even click on the lines to see exactly what county it is. This one's Tillamook. I wonder what this one is. This is Coos and Jackson. And you can right-click these to make them go away. Again, they'll go more in depth about each functionality, but this was just a quick demo on how the program works.
Hello, my name is Hanson. I'm going to be covering some of the material that I worked on in the project. Firstly, starting with the statistical tools portion. In this section, I worked on the calculations for the error in the line calculated by the program in the graph. The structure of the data frame made modular increases to data types and different data values moderately difficult. To work around this, I worked with the raw data as it was intercepted in the export to CSV functions. With the raw data, I was able to do calculations on the input values used in the error in the polynomial regression line. This sort of workaround works, but if further data or information is wanted in the export CSV file, a more modular structure of the data frame would allow you to introduce new data types and new data values without having to intercept the data and haphazardly inject it into the data frame midway, as opposed to having a modular object which you could add these data types to in a more robust manner. This would allow further increases in the life of the program to be implemented. However, this would require an overhaul of the architectural structure as it stands for the program. The second portion of code that I want to talk about that I worked on was this little bit smaller bit of code where I worked on reformatting the list of data that was used in the export to CSV function. Originally, this list used to hold all of the exported data was a statically bound list, and this would result in a data overflow where any information exceeding the list size would be truncated from the export to CSV file. So in order to combat this, I reformatted the list so that it would be dynamically built based on the arguments passed into the function, and this would allow the export file to contain the exact size list needed for the export.
I'm Christopher Snow. I'm going to go over the user interface changes first. When we got the program, the user interface definitely had some problems. The UI was written so that it was always displayed at the exact same size. When the original team had built it, it had turned out that the UI was too big to fit on our sponsor's screen. This term, our sponsor had a new larger monitor, and where the program had been too big before, now it was way too small. Clearly having the program operate at a fixed size wasn't working out. So what we decided to do was to redesign and rework through the whole program UI. I helped to take everything that was static and change it so that it was able to dynamically change size depending on the size of the screen. This was an ambitious undertaking, even more so as other team members developed more features that needed to be added to the interface as we went. I'm definitely proud of our results here though. You can see a few of the initial problem areas that had to be addressed. On a small screen on the left, the graph would start to cover up important parts of the interface. Buttons would be pushed to unexpected and inaccessible places, some beginning to disappear off of the screen entirely. On large screens on the right, the space around the program would continue to simply expand, leaving the program tiny in the middle with large amounts of unused space around the sides. After updating the UI, you can see that things look much better. On the small screen on the left, nothing is covered up or inaccessible. Even though there's more buttons and choices than before, everything scales down and continues to fit well. On the large screen on the right, you can see that the UI elements grow with the program, allowing the graph to expand and for everything to be larger and more visible, and the program fills the whole window as it should. The issues with the original UI ended up stemming from several different problems, each of which had to be solved. The first and clearest issue was that everything in the interface was defined in terms of absolute pixels, the window size, all the buttons, everything. Upon a closer inspection though, the problems were a little bit deeper than that. The elements of the UI had all been added without being configured correctly, which meant that the layout of the original program had not actually been as intentional as we had thought. As an example, in one location, an attempt to set a group of 8 elements had instead resulted in the first element of the group being set and reset 8 times in a row. Elements that had been successfully moved from their default positioning hadn't been moved by assigning them to a grid location. Instead, they had been moved by adding more static pixel offsets to the elements, moving them in appearance without actually changing which part of the UI the elements were anchored to. Our work involved solving all these problems. We successfully reattached all of the UI elements as part of a dynamic scaling grid. We removed all of the positioning offsets and attached each element to the correct row and column of the grid. And we removed as many of the hard-coded pixel values as possible.
Hello, my name is Vinh, and I'll be highlighting 2 of the tasks that I worked on during this project. So the first task is the y-axis scaling. Here I collaborated with Christopher, and our goal was to allow users to define their own upper and lower limits along the y-axis when generating a graph. The other task was the save state, and that one I worked with Gabriel and Christopher as well. And our overall goal here was to save the current state of a program before termination, and then later on allowing the user to import that same state back in and work with that set of data however they want. So starting with the y-axis scaling, the problem was that the program would always auto-scale every graph generated without letting the user set any limits along the y-axis, but they had the ability to do it along the x-axis. So similarly, we added these input text boxes that would allow the user to input and define their own limits. As you can see on the left-hand side, if left empty, the program will auto-scale for us, but we can also do our own defined limits on the right-hand side. And we did this because we didn't want to restrict the user working with one or the other exclusively. So this is an addition to the set of tools that this program has, and it's a nice feature. All right, moving on to the save state. Here, our client wanted the ability to work on a set of data that they previously worked with, but they had no ability to do that, right? Because all that data would be lost as soon as the program quit. So what we came up with was we would serialize the current data frame of the program by using the pickles library supported by Python, where we essentially would just export everything that's on that page into a byte stream and then later rebuild that byte stream when imported back in. In this example, I'm saving a test file of all the parameters that is set in this current data frame. And here we can see that when I import into an empty program in a new tab, it restores everything on the right-hand side from the plot and the data table itself here of the counties and states, along with the type of graph and the type of data that we're working with. Another requirement that came along was the client wanted the ability to save just the data table itself into a text file, and then have the ability to edit that text file if they wanted a separate editor. And so what we did here is that we exported just this data table of counties and states and county codes. And it was fairly simple. We just exported that into a text file. We formatted it accordingly here in this example. So in this example, we're actually importing these test files, but they're text files. And you can see that on the left-hand side, I'm only importing one text file, but on the right-hand side, I'm importing two. So the program has the ability to import multiple files, and it takes into account of duplicates of states and counties, and it makes sure that nothing is duplicated, and that helps with any strange behavior in the data set that the user may be working with. And here's the example. Once imported, it combined both text files of states and counties, and then on the right-hand side, you can see that the user is able to work with that set of data by adding their own parameters in the rest of the program.
Hello, I am Theo, and I would like to talk about the two tasks that I worked on for this Capstone project, and specifically highlight them in the light of the difficulties of working on existing projects, as opposed to building something from scratch. First, I rediscovered the build process that the previous Capstone team used to create the executable, and second, I worked on adding additional data to the program's export CSV function. For rediscovering the build process, that was something we needed to get out of the way very, very quickly. Our client wanted a program that they could easily run by just clicking an icon on their desktop. The previous team figured out a process which allowed them to change their raw code into a little clickable, but when we were handed that project, we didn't find any explanation of how they did this. This meant that while we could update the program and showed it to our client by running it ourselves in our own more involved developer process, we couldn't actually make those changes into something our client could use. I started figuring out how they did it by just reverse image searching the program's icon on Google Images, because it looked kind of like a generic little floppy disk. Sure enough, it was a little utility called PyInstaller that I found. After messing around with it and using it to build a few scripts into little executables, I was fairly certain that PyInstaller was the tool that the previous team used. From there, it was just a matter of troubleshooting and getting PyInstaller to build our project correctly, which was mostly trial and error. I run PyInstaller on a code, run the resulting executable, and try to figure out why it crashed. Most of the time, it was just a missing requirement or something. Eventually, I discovered a process that consistently installed PyInstaller, all of the program's requirements, and successfully built an executable. I've since written down this process and added it to our project repo's README, which will hopefully save a future Capstone team some time. Rediscovering the build process was not something I should have had to do. I had to do it because the process wasn't written down, or if it was written down, that information never made its way to us. This just highlights how important documentation is when you're working on a project that was handed to you and that you intend to hand on to someone else. As for the additional data task, I expanded a feature of the program which lets users save the data they're looking at in the program into a CSV file, which can be used in programs like Microsoft Excel. Our client wanted this file to contain some additional data to make certain types of statistical analysis a little bit easier. The largest difficulty in this task was that the program was not built with expandability in mind. The code that gathered and formatted the relevant data was particularly unwieldy, with lots of long runs of branching code. Ideally, the additional data would have been gathered and processed in this step, but getting the information out of this section of code would have been difficult without significant rewrites. So I went with a workaround where I intercepted the existing exported data right before it was written to the CSV and performed the necessary calculations there. This required some code that would interpret the various forms of the exported data, but worked well in the end. More specifically, the program creates a CSV by first building a data frame, which is a data structure from Pandas, which consists of a two-dimensional table of rows and columns. The data frame is of arbitrary size, which works really well because the rows and columns required to hold all the data change with the type of data we want to export. For example, adding more counties adds more rows, and exporting the polynomials of a higher degree requires more columns. The data frame also has a built-in method to export to CSV, which makes it really, really good for this purpose. The issue, however, was that to be able to interpret data from a data structure of arbitrary size, where the rows and columns change with the data represented, I had to write some code to do so. This workaround wasn't particularly difficult to create, but it would have been much easier and much more elegant if the program was built with expandability in mind, or if these features were part of the goals of the team that built the program in the first place. This task also represented another challenge of expanding a program built by another team. Our client wanted us to add features to the program that the original team could not have known about, and as such, the original team made some decisions that impacted our ability to expand the program. This is not to say that the original team did a bad job. They did an excellent job of meeting the goals set out before them, but rather to say that expanding existing projects beyond their original scope creates unique challenges that one must be prepared for.
Hi, I'm Gabriel. A couple of things I worked on are the executable build process and save state. First, I'll cover executable build process. Since I believe Theo and Dylan already covered this in detail, I'll be brief. Basically, it involved rediscovering what the previous team used to build the program executable, and learning how to use it. The previous team used a Python extension called PyInstaller, and by reading through the official documentation and some trial and error, we were able to reproduce the process to build the climate data program. Now I'll cover the save state. Basically, we needed to find a way to save the state of the program after a given run. Here's what a run looks like. Ideally, we can restore all of that. This can be broken down into three categories: the graph, the table of counties, and the other various graph options. For our first iteration, we focused on restoring what the program produces, the graph. This involved taking all the variables needed to produce the graph and saving them to a file in a way that we could use later. Let's break it down further. Exporting the data. The variables needed were complex objects. To gather them together, we stored them all in a pandas data frame. After exploring some options, we found that the best way to save the data frame to a file was to pickle it. Then we exported the pickle to a file. So to summarize the exporting process, we gathered the variables into a pandas data frame, pickled the data frame, and stored the pickle in a file. And similarly, to import the data into a graph, we extract the pickle from the file, extract the data frame from the pickle, extract the needed variables from the data frame, and load them into our graphing function. I added some buttons to the UI that lets the user do this. Once this was complete, we arranged a meeting with Bob, our team lead David, and my partner Vinh. I demoed it for Bob, and we got some good feedback about what direction to take. Bob wanted to be able to operate on the save state. This means restoring the table of counties. Bob didn't require us to restore the various graph options, as he'll change them anyways while operating on them. So for our second iteration, our direction was set. Restore the table. This involved saving some additional variables in a file for later use. Let's break it down further. We built off exporting the data. To gather the additional variables together, we added them to the existing pandas data frame being used to restore the graph. Again, we pickled the data frame and saved the pickle to a file. Then similarly, to import the data into a table, we extract the pickle from the file, extract the data frame from the pickle, extract the needed variables from the data frame, and load them into the table. At this point, we received an email from Bob giving us another direction. He wanted the table to be saved and restored from a text file. To meet this, Vinh and I met and did some pair programming to add this feature. We repurposed our existing codes to import and export using a text file, and I added some more buttons to the UI. Once this was set, we arranged another meeting with David, Vinh, myself, and Christopher, who was added to the group. This time, Vinh took the turn to demo our program to Bob. More was added to save state in parallel to this, but this covers the part of save state that I worked on.
Hello, I am David, and I will now be talking about how we actually accomplished the tasks in this Capstone project. We initially focused on meeting with Bob and understanding the program more, and tried to narrow down what milestones would improve the project in terms of usability and what Bob actually wanted to be added. We completed some of the smaller tasks first, since it was very difficult to implement features while working with code that we have never seen before. The first task, implementing the y-axis manual input, allowed the team to get familiar with user interface, the graphing portion of the program, and more generally, GitHub as a whole, which proved to be very successful as most tasks that needed to be completed interacted with user interface in some fashion. We used an agile approach in which we broke down the project into smaller subsections to be completed. This was specifically done by implementing sprints, where the team would meet once a week and discuss the progress being made and what challenges they were facing during that sprint. This was done by using Rike as a tracker for each task that we were either working on, finished, or needed to revise. We would then deliver the program to Bob in multiple iterations, building upon the program by completing more of the milestones. Bob was a crucial part of the development schedule as he would immediately begin testing the program and give us crucial feedback. Hello, this is David speaking, and I will be talking about unexpected events and lessons learned. An unexpected event that occurred, which was one of the most difficult parts of the development process, was mediating between myself, being the team lead, the actual team itself, and Bob. I would meet with Bob frequently one-on-one, which meant I had to interpret what Bob wanted and then give my version to the team. We eventually figured out meeting times that worked for different members of the team to make development much smoother. This was crucial in implementing some of the larger features, such as safe state. The team had multiple demos to present to Bob to get a better idea of what direction to go in, since the team could not afford to continue revisiting the same task as it would be too costly in terms of the time we had left to complete the project. Scope creep was a mix of both an unexpected event and a lesson learned. I would meet with Bob once a week as a team lead to really make sure his experience was as smooth as possible. Unfortunately, one of the side effects of doing so was Bob was always coming up with more ideas, which is great in terms of the project and future development. However, it began to add a layer of stress to the team as some of the milestones changed in terms of complexity. As a team lead, I had to make sure I was protecting my team from this while still meeting with Bob and trying to communicate with him that some of the tasks would not be possible in this iteration. Documentation. The necessity and importance of documentation was the largest lesson learned for our Capstone team. We initially struggled to get started on the project since it was many of our first time working on a project that we have never touched ourselves. We spent weeks as a team going through the codebase to begin to even understand how the program functions. This proved to be beneficial to us when we eventually got to implementing, but it could have been a simpler task if there had been more documentation. Hello everyone, this is David, and this is the future for the Climate Data Analysis Program. Batch mode. This is Bob's idea to have the software automatically run files that are in a subdirectory. The program would be able to have folders full of runs that he would want the program to automatically input and run based on the parameters that he would set. This would be an amazing feature that would really automate the research process. Online/web-based application. Ultimately, this program could prove to be very useful if it were to be a web application where users from anywhere in the country could run their own tests to see how their own local areas may be affected by climate change in the future. More types of climate data. Introducing a larger variety of climate data such as ocean warming, sea level rise, wind chill, and heat index. These could all prove useful to Bob in the future, allowing him to do more analysis on a larger spectrum.
It's been really fun working this term with David Motorca, Christopher Snow, Dylan Hanson, Theo Nguyen, Vinh Duong, and Gabriel Sampang. Their job in this capstone was different from most other students because rather than writing a new program from scratch, which is pretty easy because you know what you're doing from the beginning, what they had to do was continue the development of a really complex program that had been developed by a previous capstone team. Now, when this term's team got into it, they were making a lot of improvements, but the first step was to figure out what in the heck the previous students had done. Now, you can look at the results of the program, what it does, how it runs, but looking at the mechanics behind it, it's almost worse than writing a program from scratch, because if you start from scratch, you decide what you're going to do, but in this case, before they could do anything, they had to figure out what the previous students had done. And of course, being students, this previously written program wasn't just a smooth finished product. It had all sorts of add-ons and so forth. So I've been really impressed how they got into this. Actually, I was impressed that they selected the program for this capstone in the first place. But getting into it and first figuring out what had already been done was, a super challenge. And I'm really impressed with the way they managed to decipher all the existing code and then rather seamlessly add all the wonderful improvements to it. So it's been a real pleasure working with this group of students.
Lastly, as a team, we just wanted to say thank you for the opportunity to work on this capstone, and more specifically, a big thank you to our sponsor, Robert O'Brien, for being an amazing sponsor and always being communicative and flexible with us.